Hi guys, today we're going to talk about Chapter 8, Earth Systems and its Resources. And this is a lithium mine in Bolivia. Doesn't look like a typical mine, does it? The opening case study compares the internal combustion engine with a hybrid electric vehicle. So unless you have a green hybrid electric vehicle, you are driving an internal combustion engine. So the question is, are these electric vehicles really as environmentally friendly as we think? And even though we reduce our consumption of liquid fossil fuels when we use hybrid electric vehicles, they do come with some trade-offs. For example, you have to mine neodymium, lanthanum, and lithium for the batteries. And that causes all kinds of disruptions to ecosystems. Creates holes in the ground, habitat loss, potentially acidic water from acid mine drainage, just to name a few. So the resources that we need and that we use on Earth were determined when the planet formed about 4.6 billion years ago. The layers of the Earth contain those different resources that we use. First of all, the core, which is the innermost zone, is made of nickel and iron. And the mantle above that has the liquid rock we call magma. The outer crust is the outermost layer of the planet. And if you look at this image, you can see these layers broken down a little bit more. Got the solid inner core, the liquid outer core, the magma, the mantle. And then you've got the mantle that's broken down into the crust, the lithosphere, and the asthenosphere. The distance to the center of the Earth is about the distance from Los Angeles to Halifax. So the asthenosphere, which is the outer part that I just mentioned, is composed of semi-molten rock, and the lithosphere is the brittle outermost layer of our planet that's approximately 100 kilometers thick. Convection and hot cells are an important part of our system that creates rock and makes new rock, or I should say recycles old rock. So if you look here, these are convection cells underneath, and so the Earth is very hot at the center, and as this heat moves in these cycles, it causes plumes of hot magma to well up in the mantle. So this circular motion is what creates this welling up of the magma. And so that is where new lithosphere is being created. So if you look at these arrows, you can see, and we call this area called a spreading zone or seafloor spreading. So you've got arrows moving this direction and arrows moving this direction. This is an oceanic plate or oceanic crust, and it's subducting under this continental crust because it's more dense than the continental crust. So this is, land right here, as well over here. On this side, however, you do see that there's rising magma, so there's a weakness here that's getting pushed up and creating a volcanic chain. So that leads me to the theory of plate tectonics, which is a theory that states that the Earth's lithosphere is divided into plates, most of which are in constant motion. And in 1912, Alfred Wegener, he pinned the name Pangaea for one giant landmass that scientists reason was, the structure of our land at that time. And then through this seafloor spreading, we created these new continents. And he based this idea on the fact that they found fossilized evidence of the reptile Mosasaurus in South America and in the southern tip of Africa. And if you look at the two continents, it's pretty clear that they were at one point joined. Plate tectonics are moving, and in this image, you can see that the arrows indicate the movement of those plates. You have areas where seafloor is spreading, that's the orange, and that's where new lithosphere is being formed. And then you have areas where plates are subducting, that's the blue, and that's where old lithosphere is being recycled back into the mantle. And the other thing that you want to look at on this map is just also the direction of the arrows. The arrows are showing the direction of the plate movement. Where you have, like I said earlier, oceanic plates and continental plates meeting, you have an area of subduction, and where you have two continental plates meeting, you have mountain ranges or volcanoes forming. Volcanoes are formed as plates move over hot spots where there's rising magma. And so the Hawaiian Islands are an example of this. The island of Niihau, which is the furthest one, was created about 4.89 million years ago. And it was originally over the hot spot, which is right here. And we have a new island that's forming over the current hot spot named Lohi. But that's how all of those Hawaiian Islands formed, as that hot magma was rising up. So we have three different kinds of plates on Earth. There are divergent plate boundaries and convergent plate boundaries, and we have transform fault boundaries. So let's take a look at these. A divergent plate boundary is what I kind of mentioned before when you have magma rising up and you have seafloor spreading, but it can happen in other areas too, where continental land masses are actually breaking apart. So we would call this divergent because those areas are moving away, those arrows are showing movement away from the center. A convergent plate boundary is where two plates are coming together, and then a transform fault boundary is where two plates are actually slipping past each other. An example of a transform fault boundary is the San Andreas Fault in California that runs from the Northern California area to the Southern California area. And so a fault is actually just a fracture in the rock across where this movement can occur. And the earthquake is something that occurs when these rocks rupture unexpectedly along the fault. And so if you look here, this is an actual image of the San Andreas Fault. And we know that California has been riddled by earthquakes in its past, and a lot of people that live there are always thinking, well, when is the big one going to happen? Because as these plates move past each other in a transformed fault boundary, it creates this massive explosion in the form of an earthquake where the ground literally rumbles and rolls. And that's just because there's no subduction going on. There's just slipping past one another. So the fault zone is where the largest expanse of rock has moved. The epicenter is the exact point on the surface of the earth directly above the location where the rock has ruptured. And the Richter scale is the scale that we use to measure the magnitude of an earthquake, and it's on a scale of 1 through 10. The scale increases by a factor of 10, so an earthquake that you would see that's measured as a 7 is 10 times more great than an earthquake of 6. So the Ring of Fire is this area that circles the Pacific Ocean along plate boundaries, and you can see it in this purple area. And there tends to be an awful lot of earthquakes and volcanoes in this area, if you look at it compared to the rest of the earth. So it's this whole region, lots of earthquakes, lots of volcanoes. So just remember Ring of Fire. So the rock cycle is the constant formation and destruction of rocks. And so just look at this image. You've got that liquid mantle that creates the magma in those cells that I was talking about before. And as magma moves to the surface, it cools and crystallizes and can form igneous rock. If that igneous rock is put under heat and pressure, which it is when it stays underneath the surface of the earth, that heat and pressure can change the rock into what's called metamorphic rock. Some examples of igneous rock would be granite and basalt. So if you've got granite in your house, that's an igneous formation. Or if you have marble in your house, that's a metamorphic formation. And then when these get pushed to the surface, weathering and erosion can break down parts of the rock and transport it, where it can get laid down in an ocean and into layers and form sandstone and limestone. So this just explains those different types of rocks, but you can read this a little bit more if you want to. And I want to show you this image that shows how sedimentary rock forms. So like I mentioned earlier, as that rock gets broken off through weathering and erosion and gets transported to the ocean, layers get laid down. And then pressure and heat can compress it and form sedimentary rock. Igneous rock can form two different kinds, igneous intrusive and igneous extrusive. Intrusive is formed underneath the surface of the earth and extrusive outside. Some examples would be obsidian, gold, and lanthanum. Here's another image of sedimentary rock formation. And so just sediment building up over time, compaction occurs. You've got layers that then form, and then you've got cementation that occurs because salt crystals in the water actually glue the layers together, forming one solid rock. And the weathering and erosion that I talked about before occurs when air, water, and certain chemicals or biological agents actually degrade the rock into soil. And so here we have an image of a rock that's probably had a little bit of a depression, and it formed a crack, and then eventually a plant seed got in there and grew from that little bit of soil that was found in that crack. Weathering and erosion can also be chemical, and so this is when there's a breakdown of rocks and minerals by chemical actions. So, for example, water that contains carbonic acid, which is CO2 and water together, it can wear away limestone and form really spectacular cave structures, like this cave right here with these fabulous stalactites and stalagmites. And then you can also have these immense craters form, or sinkholes. So that's where in this area, this is called karst topography, where the limestone has been eroded away underneath the surface, and then all of a sudden that surface gets weak and it collapses. Erosion is the physical removal of rock fragments from a landscape or an ecosystem through wind, water, and ice. And living organisms can also erode these materials. Deposition is where that eroded material accumulates or is deposited. So I like to show this image because it's really clear. You can see the layers of sedimentary rock over here that have been laid down over time. And then you have, and it's solid. And then in the beginning or the front of this picture, you can see where there were weaknesses in those rocks where water had hit, and then it created these little cracks. So that's erosion, and then deposition in the back. Acid deposition is acid rain, sleet, snow that has it's carbon dioxide mixed with water, so carbonic acid. You can have nitric acid, sulfuric acid. So today in the United States and countries with large cities, we have an immense amount of pollution that's being emitted into the atmosphere, and that pollution can form secondary pollutants in the form of acid rain. We'll talk about that a little bit later. Soil is important because it's a medium for plant growth, and it serves as a filter for water. It's a habitat for living organisms, and it also filters pollutants. It also breaks down organic matter and recycles nutrients. So if you take a look at this image, that's just all of these different things that we need soil for. And these different layers are called horizons. We'll talk about that in a minute. Soil forms through the formation, I should say, of soil forms because of a bunch of different things that have to be, that are intact. The parent material or rock material makes the soil. The climate also contributes to the type of soil. If it's a warm climate that has a lot of decomposition and breakdown of nutrients, you're going to have a different type of soil than you would, for example, in maybe the boreal or the tundra, where you don't have warm climate, and so there's not a lot of decomposition going on. The topography is the surface and the slope where the soil is forming. So if you've got steep slopes, and the soil can't stay intact for very long because of runoff, then you're not going to have very fertile soil. The types of plants and animals also contribute to the fertility of the soil, because as plants and animals die and decompose, they put nutrients back in the soil. And then, of course, the time that the soil has been developing can determine its properties as well. If the soil has been functioning for a long period of time, you're going to have a lot more nutrients in it. And then the last thing are the geological processes or glaciation. So glaciers can also contribute to different types of rocks. So let's look at the formation of soil in an image here. So you've got very immature soil, meaning if you look at the top, there's not much soil, and you've got this parent rock below. So the parent rock is weathered and fragments move up towards the surface. And as that soil gets deeper and deeper, and you move along in time here, you can see that soil's getting deeper. You have organic material that accumulates as plants and animals die and contribute to that organic matter. And then a very mature soil would have greater amounts of organic matter present and could support larger plant species. Soil is made up of soil horizons, and they form as the layers of the soil develop. And so at the bottom here, which is the C horizon, you have the least weathered portion of the soil profile, and this would be similar to the parent rock that would be found below it. The B horizon right here is the zone of accumulation that has metals and nutrients found in it. And then you have the A horizon, which is a zone of overlying organic material that's mixed with underlying mineral material. So you have this pushing up and this pushing down. And that's the area we would consider to be the top soil. And then the O horizon is primarily composed of organic matter. So we sometimes refer to that as humus. And some soils, an E horizon can occur that would be found either between the O or the A horizons. So soil has physical properties, and texture is one of them. And the texture is the percentage of sand, silt, and clay that the soil contains. And so all soil has some amount of sand, silt, and clay. Well, I shouldn't say that. I mean, we want to look at what are those percentages. Soil that has 40% sand, 40% silt, and 20% clay is considered a loam, and that is the healthiest soil for agriculture in most situations. So you can look around this little triangle and look at these different percentages. If you have less percentage of silt, and you might be talking about a clay. If you have greater amounts of silt, you might just have a soil that's just silt. So depending on the percentages of sand, silt, and clay, you will have a different type of soil. This just shows you the differences in size of sand. This would be sand, silt, and clay. It's just relatively showing you that clay is very small and sand is much larger. If we look at the porosity of soil, which is another physical property, the porosity is how quickly the soil drains, depending on its texture. So sand has very large, loosely packed particles that drains very quickly. Silt has smaller particles that drains a little bit slower, and clay has very, very tiny particles that are packed very closely together, and so clay does not drain very quickly at all. We use clay in landfills because of that texture and the fact that it doesn't drain very quickly. So chemicals are not going to leach out. CEC is the cation exchange capacity. So this is a chemical property of soil. And that is the ability of a soil to absorb and release cations. So those cations are what we would call positively charged mineral ions. So there are soil bases and soil acids. Bases would be things like calcium, magnesium, potassium, and sodium, all elements you find on the periodic table of elements. And then soil acids would be aluminum and hydrogen, for example. So the base saturation is the proportion of soil bases to soil acids. So knowing the CEC is important because farmers can amend their soils when they know that they have more bases or less bases, or likewise with acids. So bases tend to be more advantageous for agricultural soils than the acids do. But it also depends on what part of the world we're talking about. Because different plants need different things to survive and to grow in. Some biological properties of soil are that we have lots of organisms that comprise our soil profile. So 80% of the organisms you find in soil are fungi, bacteria, and protozoans. Rodents and earthworms also mix the soil, and then you have snails and slugs that eat the plant roots. And then if you look at the majority of the organisms you would find in soil, you would say that most of them are detritivores, which are breaking down dead organic matter. This is just a soil food web. I wanted to point this out to you to show you that it's a very complex system and we need to protect it. So dumping caustic and hazardous chemicals on the ground is never good, as well as not putting it in water. So it ends up somewhere and can impact biodiversity. Soil degradation can happen a couple of different ways, and this is just the loss of soil's ability to support plant life, and erosion is one. So this is when the topsoil has been disturbed and the vegetation has been removed by either wind or water that's been eroded away or eroded the topsoil. And it can occur in a single season but take centuries to be replaced. So this is just showing you some erosion that has occurred that has created this big river system. So the river at one time was at the same height of these two landmass or rock masses here at the top, but it's eroded the softer rock away to this level right down here. Compaction is another way that soil can be degraded. When soil is compacted, it then can dry out because water can't infiltrate, and it can happen because of machines, animals, and humans. When you have machines are pretty straightforward, driving on soil compacts it, but animals like cattle and other large animals can compact the soil as well, and humans as well can. And you've seen that when you've walked on trails, you can see that beaten down path where vegetation can no longer grow because the soil is so compacted. Compaction depletes nutrients, and then consequently we have to use pesticides in order to grow things, and then those pesticides can pollute the soil. This is just showing you the difference between soil that has a lot of air and water space, so that air and water can get in. It's not compacted, and this is compacted, not allowing for air and water to get into those pore spaces. Some other types of erosion, just again, erosion of water carving out a valley. Along the ocean, waves can cut back banks and create cliffs. You have wind that can blow the topsoil off. You have glaciers that can move boulders and move rocks. And you have landslides that can occur. Soil compaction creates less airflow and water space, like I mentioned before. And I just wanted to show you this image. This is compacted soil that doesn't have rich soil. Look at how pale it is compared to this really rich humus and layers. The horizon is packed with lots of nutrients, and look at how much thicker the vegetation is. So again, just soil compaction, not good for soil. It can also lead to erosion and water runoff in this cornfield, for example, after a brief rainstorm. So they had compacted this, planted the corn, and just driving over it and over it and over it, compacted it so much that when there was rain, the rain had nowhere to go, and so it ran off. There's an uneven distribution of mineral resources, which has social and environmental consequences to us on Earth. You know, we have ores that are concentrated accumulations of minerals, like metals, salts, and sands. And we have metals, we can break those down even more into specific elements that have properties that allow us to use them for conduction of electricity and heat. Some examples would be copper, nickel, and aluminum. And this just shows you some the greatest distribution of the most abundant mineral resources that we have on Earth. Reserves is the known quantity of a resource that can be economically recovered. And this shows you the global reserves and the US reserves remaining in years. But this was published in 2007, so we're far past that. At that time that it was published, aluminum only had 2 years in the United States, so we can make the assumption that we no longer have aluminum for us in the United States. So consequently, we have to rely on other countries. China, for example, is the biggest exporter and producer of rare earth elements, so REEs, rare earth elements. We use these REEs for all different kinds of things like fluorescent lights, wind turbines, solar panels, radar systems, lasers, medical imaging, electronics, and hybrid electric car batteries. So I just want to point this out that China its share of rare earth elements is so much greater than other countries. And so consequently, we depend on China for positive relations. We've got to be friends with China in order to get the things that we need to live the type of life that we want to live, with all of the amenities that we have with cell phones and technology and medicine. This just shows you some of the other elements that are needed, or minerals that we use in order to run an electric car. I talked about that earlier in the case study. So that leads me to how we get those resources, and that's through mining. Surface mining, which is the removal of minerals that are close to the Earth's surface, or strip mining, which removes strips of soil to expose ore. Open pit mining is the creation of a large pit or hole in the ground that's visible from the surface, or mountaintop removal, which is removing an entire mountaintop, and placer mining, which is looking for metals and stones in rivers and sediments. And so here's an image of that, these different kinds. So you've got mountaintop removal, open pit, strip, placer mining, where you use, this is called a sluice box, where you dig out soil in a bank, put it in here, and the water will erode away, take the lighter soils out, and leave the heavier metals. For example, gold. This is one way that gold panning was done, or gold mining, I should say. And this guy that's bent over has a pan, and he's gold panning. You can also create subsurface chambers where you can mine inside of a mountain, where you create, and you can use elevators to get there. So you got to dig these shafts and then drill horizontally to get in there, to get to veins of gold and silver and molybdenum and whatever. So this chart, I want you to read it on your own time, just compares the difference between surface mining and subsurface mining. So this is surface and this is below the surface, and its effect on air, water, soil, biodiversity, and humans. This has come up in FRQs before, so make sure you read this in the book, because it's very important to think about all the hazards that mining has on humans and biodiversity. Here's the Kennecott Bingham Canyon copper mine. And it's an open pit mine near Salt Lake City in Utah. It's really immense, almost 2.7 miles across and 0.7 miles deep. So it's just this huge scar on the land. A lot of biodiversity and habitat loss because of this mine. But they're mining copper, which is something that we need based on the way that we live our lives. Acid mine drainage is what happens when mines are abandoned. And so during the mining process, pyrite is exposed. Pyrite is a type of rock. It's also called fool's gold. Groundwater seeps into the mine, and then oxygen and water combine with that pyrite, and they react together to form sulfuric acid. And that acid dissolves metals from rocks. So any metals that weren't taken during the time of the operations of the mine then get dissolved. The rock gets dissolved and the mines are liberated. And then the water drains out of the mine, and the dissolved metals react with oxygen and they fall out into solution in the stream, and they turn the stream a bright color, and that affects aquatic organisms and plants, oftentimes causing massive kills. The Argo Gold Mine is in Idaho Springs. They do tours. It'd be a fun tour for us to do sometime. They even do them on Saturdays, so maybe that's something we could talk about. This is just showing you the zones of tolerance of organisms with regard to acid mine drainage. And in a nutshell, just know that most organisms need to exist close to 7, which is neutral. So anything that's more acidic than that starts to affect their ability to survive. Here's an image of acid mine drainage coming from an old mine, and some rivers in Colorado that have had acid mine drainage exposure. And this occurred in 2015, the Gold King mine blowout, which polluted the Los Animas River in Durango. So the Los Animas flows from Silverton through Durango, and this was literally the color of that water in 2015. I was super stressed watching this occur as they were talking about it on the news. In the textbook, it talks about the active mining that occurred at the Trapper Mine in Craig, Colorado. Look at the immense scar that occurred because of the mining that went on there. And it was mountaintop removal and some strip mining. But then afterwards, they reclaimed the land. To reclaim the land means to go back in and put soil back and revegetate and replant. And so you can look at how the reclamation actually resulted in such a positive outcome. And in fact, scientists found that there were new species that arrived after the reclamation process was done. This is just showing you hard rock mines and waters that have been polluted by the metals, and the mines in this image are all abandoned mines. Some of them have become Superfund sites, and some are just abandoned and nobody's caring for them. So we have a lot of issues here in Colorado. We were a very rich state with lots of mineral opportunities, and people definitely took advantage of that. That's it for Chapter 8. Have a good day, guys. Bye.